Hey folks, my name's Nathan Johnston, and in this video I'm going to show you how you can use linear algebra to do polynomial interpolation. In other words, if you're given a set of points, I'm going to show you how you can use linear algebra to find the polynomial of lowest degree that goes through all of those points. To ease into this and sort of give you an idea of how the method works, let's start off with the problem of finding a line that goes through the 2 points, -2, 2, and 4, -1. In other words, we want to find the equation of the line y equals ax plus b, whose graph goes through those 2 points. Now, this is a simple enough version of the problem that maybe you already know how to solve it. You might be able to just sort of eyeball a solution by doing graphing sort of stuff like up here. Maybe you know an explicit formula for how you can fit a line between 2 points. But we're going to see how we can solve this problem via linear algebra because the method that we use is going to generalize to harder versions of this problem. Okay, so what we're going to do is we're going to realize that, hey, if I want a line to go through those 2 points, if I want y equals ax plus b to go through those 2 points, then when I plug those points into that equation of the line, I should get a true equation. Okay, so for example, if I plug -2, 2 in, that means I plug in x equals -2 and y equals 2, so I get the equation 2 equals a times -2 plus b. And the reason that we're going to be able to solve this via linear algebra is that's a linear equation there. Okay, you have to flip your thinking a little bit because you're used to thinking of linear equations as involving the variables x and y, but x and y are not variables here. Those are given to us. We were told x is -2 and y is 2. They're not variables anymore. Instead, the variables in this linear system that we're going to construct are a and b, right? Because those are what we're trying to solve for. We're trying to find the slope of the line a and the y-intercept of the line b. So those are the variables. And then we do the exact same thing with the other point. We plug the point 4, -1 into the equation of the line, and we get -1, the y value, equals 4a plus b, where 4 is the x value. So at this point, we have a linear system, so we can do what we always do in linear algebra. We take that linear system, throw it into a matrix, row reduce it to find the solution, okay? So when I throw it into the matrix, remember the columns correspond to the variables. So that first column, those are the coefficients of the variable a. The second column has the coefficients of the variable b. And then we just do our row operations, okay? I've got a leading entry of -2 in the top left corner. I just add double that top row to the bottom row to get a 0 down below it, okay? And then I just keep going all the way until I'm in a row echelon form that's sufficiently simplified that, I'm happy to work with it and find out what my solutions are. Okay, and at this point, the matrix is in row echelon form, so I could stop here if I wanted to, but I'm going to go one step farther just so that I don't have to back substitute afterwards to find my solutions, to find my a and b. Okay, and then at this point, I can see, okay, that top row there, that top row of the matrix, that tells me that -2a equals 1, so just rearrange and solve a is -1/2. Similarly, the second row of that matrix, that tells me 0a plus b equals 1, so, well, b equals 1. There's nothing to even really solve there. Okay, so yay, we know our a and b values now. The line that goes through those 2 points, it's y equals ax plus b. Well, in other words, y equals -x/2 plus 1. And if we just go back up to that line that we plotted a moment ago, okay, the line that we found that goes through those 2 points that we found sort of geometrically, of course, it's the same thing, okay? That is the line that we found earlier. Okay, so fine and dandy. In a sense, we didn't learn anything new there. You probably already knew how to find a line that goes through 2 points. But now let's ramp up a little bit. Let's go on and see how we can generalize this method and, for example, find the equation of a parabola that goes through 3 given points. Okay, in particular, let's try to find a parabola that goes through the points -1, 1, 1, -3, and 2, -2. In other words, I want to find the parabola with the equation y equals ax squared plus bx plus c, whose graph goes through those 3 points. So I'm trying to find the a, b, and c here that do the job. Okay, and I can try what I did before, just fumbling around geometrically and hoping to stumble on the correct parabola, but it's much harder this time. I've got 3 separate parameters that I can vary rather than just 2, the slope and the y-intercept. Okay, so instead, let's do the more systematic thing. Let's turn this into a system of linear equations and try to solve it via linear algebra, just like we did for a line going through 2 points a moment ago. Okay, so again, just mimicking what we did earlier, I'm going to plug the different points into the equation of the parabola. I'm going to plug them into y equals ax squared plus bx plus c. And so, for example, if I plug the point -1, 1 into that equation, I get y value equals, well, just plug all the x values in on the right-hand side. So, for example, the y value is 1 here, so I get 1 equals, well, a times -1 squared plus b times -1 plus c. And then we're just going to simplify that down a little bit. And after we simplify it, actually do that -1 squared, for example, what we're going to get is the linear equation 1 equals a minus b plus c. And then we do this with the two other points as well, okay? We're going to plug 1, -3 in. That means we plug in 1 as the x value on the right-hand side, -3 as the y value on the left-hand side, okay? And then we just simplify that down. We're going to get the linear equation -3 equals a plus b plus c. Finally, we do that for the third point, 2, -2. We plug in x equals 2 on the right-hand side, y equals -2 on the left-hand side, okay? Just everywhere you see y, replace it by the y value. Everywhere you see x, replace it by the x value, okay? And what we get here this time is a linear system with 3 variables and 3 equations, okay? The 3 variables, again, those are the parameters that we don't know that we're trying to find in the parabola. Those are the a, b, and c. And we have 3 equations. We throw them into a matrix where, again, the columns of that matrix correspond to the different variables a, b, and c. Augmented right-hand side is just the y values, the 1, the -3, and the -2. And we just do row operations to bring it down to a row echelon form so that we can find out what the a, b, and c are. Okay, I'm not going to dwell on the particular row operations that I do here, but I'm just doing Gauss-Jordan elimination, okay? There are earlier videos where we learned how to do this, so you just do that procedure. I'm going to go all the way to reduced row echelon form just because, well, I can this time without introducing any fractions or anything ugly, so I might as well. I get all the way to reduced row echelon form, and in that top row, I've just got, that top row, that's an equation. That tells me 1 times a plus 0b plus 0c equals 1. Similarly, that second row, that tells me 0a plus 1b plus 0c equals -2, so b is -2. And similarly, the bottom one, it's 0a plus 0b plus 1c equals -2, so c is -2 as well. Okay, so that parabola that goes through those 3 points, well, it's the parabola with those parameters. A is 1, b is -2, and c is -2. It's y equals x squared minus 2x minus 2. That's the parabola that goes through the 3 points. And if we go back up to the graph, well, we can see that. Just change the parameters to the ones we just talked about. And yeah, it's going to go through those 3 points. Okay, and that's it. That's all you really need to know. This method, it'll always work. The really nice thing about this is whenever you do this procedure, whenever you construct a linear system this way, no matter how many points you are given, try to construct a polynomial of degree 1 smaller that goes through those points. You'll always be able to do it as long as the x coefficients are distinct. It turns out this linear system, it always has a unique solution, okay? And maybe that's a topic for another video. I'll show you why that's the case. All right, thanks for watching, everyone. We're going to have a bunch more of these videos still. There's a ton of other stuff that you can do with linear systems, so I'll see you around for those future videos.